One thing that perhaps I didn't focus on enough before is that the energy levels get higher and more split apart when the length of the trap gets smaller. So the smaller the trap, the higher these energy levels. We can see that effect very dramatically here in these nanocrystals. Notice we have these yellowish-whitish nanocrystals here, and these reddish nanocrystals here. These are made of exactly the same material, and the only difference is the size of the nanocrystals. Now, with a smaller size, these ones on top have a higher energy levels and therefore absorb higher energy wavelengths. In general, these crystals will absorb any wavelength that is shorter than the wavelength corresponding to a threshold energy. So when they are large, the threshold energy is small, and we absorb all wavelengths shorter than the red. As a result, only red visible light and many colors of infrared light get reflected. If we make the crystals somewhat smaller, the threshold energy goes up, so the threshold wavelength goes down. Now you have to get to a much higher wavelength before the light starts to be absorbed instead of reflected. So here we are reflecting most of the wavelengths of visible light, and we get a whitish-yellowish color. There are many other kinds of traps that we can build. For example, this is known as a quantum dot. We have a semiconductor layer in here between two insulators, which are themselves between two metals. And we can confine electrons within this semiconductor region. Here's an actual picture of one with the confined region shown right here. In this case, we can actually control the number of electrons, or at least extra electrons, within that semiconductor. And the way is by pushing them through this smaller, narrower insulator through quantum mechanical tunneling. If we make the potential high enough on this side, we can push an electron through and add more electrons. This becomes a controllable, man-made atom. It's not a true atom, but it shows many of the behaviors of an atom in that it has certain quantized energy levels inside here, and it has the advantage that we can control the number of electrons as well as the spacing of the two sides. So far we've been focusing on systems that have one prominent dimension and that they're either totally constrained or totally free in the other dimension, so we don't worry about it. But what if we had a two-dimensional system? This is known as a quantum corral, and we can build these, as you see being done in these pictures. What's happening here is that they are carefully using an scanning electron tunneling microscope to actually move iron atoms across the surface of copper. And then electrons are confined, able to move freely throughout the copper, but not able to move past the iron. And we get these very definite standing wave patterns. This is called an electron corral because it holds the electrons inside it, very much like a corral for cattle would hold the cows inside. We could imagine making one of these in a rectangular shape, length y by length x. In that case, we would need a standing wave that showed a sine function both in the x direction and in the y direction. We would, however, be allowed to have different values of n in the x direction and the y direction. The energy would then just be the sum of those kinetic energy terms for the x direction and for the y direction. Most of that factors out. It's just h squared over 8m, but then we have the sum of nx squared over lx squared plus ny squared over ly squared. We can also continue this idea to 3 dimensions, where we would have a potential trap with infinite walls along the x direction, y direction, and z direction. In that case, the energy would have a term with an nx, an ny, and an nz. In fact, if you want to do any detailed statistical mechanics and quantum mechanics treatments of systems with many particles in a confined area, such as Planck blackbody radiation or understanding an ideal gas at a more detailed level, you begin with these kind of quantum states and the energies that they represent.